Alright, so today we're going to be discussing 12.9, and it is about the Jacobian primarily, and the idea is it's a change of variables. And this is true in general when you have two or more variables. Okay? Back in Calc 1, you always said we're going to exchange x for u. So x is, some u, some function of u, whatever it is. I'm sorry, thank you. So u, rather, is some function of x. There you go. I'm going to have to talk too fast. And then du, of course, is some f prime of x. Okay? And times dx. And so the idea here is it's not a one-to-one swap. If it was one-to-one, for instance, if you wanted to integrate 3x plus 2, and you're like, I don't like x's, I'm going to change them to u's. Well, good for you, weirdo. That's a one-to-one swap. So u equals x, du equals dx. Everything's one-to-one. You just change them. Okay. However, if it was, I don't know, 3 times 5x squared plus 2, then you're like, yeah, well, u is equal to 5x. Well, then du is equal to 5 dx. So in other words, their derivatives aren't one-to-one. Okay. Well, in general, what we're going to be doing is we're going to be doing it in more than one variable. Okay, so two variables or more. So we've already talked about polar form. Okay, we are going to swap x and y for r and theta. And the reason we're doing that is because primarily we're looking down here on the x and y axis and we see this circular region. We're like, dude, polar is way easier for those. Okay, and we already know what's going to happen here, right? We already know. We talked about this before, that we're going to change our dx's and our dy's. We're going to trade them in for r dr d theta, or some, whichever direction you like to do them. Okay. Now, so that said, then, where does this r come from? Now, I explained it to you one way, but we showed it the other day in class. But if the way to do it is this, so x is equal to some function of r and theta, and y is also equal to some version of r and theta. So the Jacobian determinant, by the way, again, always positive, is given by this determinant. Now, I always like to set up my determinant the same way every time. And I like to make a little note to self on the side. Okay? So this up here is going to be dx dr, and then dx d theta. We'll continue with the same procedure all the way out throughout the whole project of this chapter. Okay, so later on we might go to u's and v's. Awesome. So we'll put the u's and v's up here. So whatever you're starting with, wherever you're going to. So when you do that, this will be cosine theta and minus r sine theta and sine theta and r cosine theta. And when you cross multiply, you get r cosine squared plus, well, it's minus and minus, plus r sine squared. And of course, if you take the r out, you get cosine squared plus sine squared equals 1. So r is your Jacobian. So in other words, we got dx and dy. We know we're going to get a dr and a d theta. The question is, what goes in front of the thing right here? And the answer is, it's an r. Okay, the same thing will be true later on. We're going to go from dx, dy, dz's, maybe something like this. Who knows? And we might want to then go to du, dv, and dw for all intents. I don't even know. So we know these are going to show up. What we don't know is what's going to go in here. Okay, so that's what the Jacobian is going to give us. Okay, not that big a deal. Now, some of the stuff that happens with the Jacobian is, some of them are cool, some of them are weird, some of them are just, plain strange. So spherical coordinates, I'm going to do that one just for fun. And so if we're going from rectangular to spherical, that's going to mean this. So we're going to be going to this, this and this. We know we're going to be going dx, dy, dz, or, whichever the 6 versions of that you like. Bleh, don't know what goes right there. That's my Jacobian. Okay, and then we're going to have d rho, d theta, and d phi over here. Okay? Again, what I don't know is what's going to go right here. And we do know that x is equal to rho cosine theta sine phi. We do know that. So everywhere there was an x in the original equation, I'm going to replace it with this thing. Everywhere there was a y, I'm going to replace it with this dude. And wherever there was a z, we're going to replace it with this guy. So we're going to make those substitutions, and then all I need to do then is, so for instance, if you had, I don't know, x, y plus z or whatever, then you would put in right here, you would just replace these guys with rho cosine theta sine phi times rho sine theta sine phi plus rho cosine theta, or phi rather. And over here somewhere you'd have a d rho, a d theta, and a d phi. Oops, a d phi. But what you don't know is it's going to go right there. Okay, so that's what we're going to be working on. Okay, again, why would you go to spherical coordinate systems? Because instead of being able to integrate over some nice, rectangular prism, if you will, where this is the z, and maybe my z's go from, 0 to 2 or something appropriate, and maybe my x's, I'm just going to pick some out here, go from 0 to 3 or whatever, and my y's go from 1 to 4 or whatever. They don't do that. No, I'm going to be integrating over, that's a sphere, but this is a sphere. I'm going to be integrating over some spherical region. And because the thing is spherical, then I want to make sure that I'm using the appropriate thing, just like with polar form. Okay? So here comes our Jacobian. Ugh. Now, I will say right off the bat, this one isn't particularly easy to mess with. Setting it up is a piece of cake. Doing it out, fortunately, you don't have to do it out. Because after you do it once, it's going to be just like polar form. You just, obviously you probably won't use it that often, so you probably won't have to do it. But if you needed to, a person could just look it up in the phone book. You can look it up in the textbook and be good to go. So this is going to be minus rho sine theta sine phi. And the last one, when you do it with respect to phi, is going to be a cosine of phi. So rho cosine theta cosine phi. And then this one here is going to be sine theta sine phi. And then this one with respect to theta is going to be just rho cosine theta sine phi. And this one's going to be rho sine theta cosine phi. And the last one is going to be cosine phi. It's going to be 0, and it's going to be minus rho sine phi. Right? Those are my partials. Now, I haven't done this by hand in a while because, well, it isn't fun. But I'm going to attempt it this morning to see what I get. So, if we're doing this, we want to take, and we're going to do these by expansion by minors. So we're going to take the cosine of theta sine of phi times, and then remember it's these guys here, so it's this times this minus that times that. So it's going to be a minus rho squared cosine theta sine phi. Right? Minus. But it's minus, it's this guy, so I'm going to make it a plus. Rho sine theta sine phi. Because this one up here is already negative. And then it is this guy times this guy, so it's going to be a negative rho sine theta sine squared of phi. Good God, I blew it right there. That's sine squared. Don't forget that. So, this times this minus, and then it's going to be this guy times that guy. So it's going to be minus rho sine theta cosine squared of phi. You can already kind of see the writing on the wall right here. You got a sine squared, you got a cosine squared. You can kind of see where we're going with this. Plus, it's going to be rho cosine theta cosine phi times. And then it's going to be this guy times 0, so nothing, minus this times this. And it's cosine theta, cosine phi, sine phi. Cosine theta, cosine phi, sine phi. Woo! What a mess, huh? What a mess. So let's see what happens here. If we distribute this, it's going to be minus rho squared. We're going to get a cosine squared theta and a sine cubed of phi. Here, if we distribute this out, we're going to get a, well, here times here is going to be a negative rho squared sine squared theta sine cubed phi plus, no, minus a rho squared sine squared theta sine phi cosine squared phi. What a mess. And the trick will be if I can do this right without dropping something. That, of course, is always the trick. And hopefully that is correct. Okay, now the fun begins. What do they all have in common? Well, they've got a negative rho squared in common. Cosine squared, no. Yeah. Do they all have a sine of phi in common? By George, they do. They all have a sine of phi in common. And that's it. So that leaves me with cosine squared theta sine squared phi plus sine squared theta sine squared phi minus, not plus, I mean plus sine squared theta. I already took the sine phi out, so it's gone. I took the sine phi out, so I'm left with cosine squared theta cosine squared phi. Whew! All right, cool. Interesting. Let's see what happens here. Let's do something else here. These two have a sine squared of phi in common. So I'm going to do this, sine squared of phi. It leaves me with cosine squared plus sine squared. And these dudes over here have a cosine squared phi in common. I can see my way home now. Whew. This is 1, and that's 1. Dude, so is this. So all of this garbage is 1, and so my Jacobian is equal to rho squared sine phi. Don't forget, it is that. It's not the negative of that. It is rho squared sine phi. The idea is this. Anytime you're going from x, y, and z to rho, theta, and phi, you're going to go from dx, dy, dz to rho squared sine phi d rho, d theta, d phi. Okay? Just like we did r before, r dr d theta, that's what you're going to have here. Okay? And it's not very difficult. It's just one of those things the guy has to just kind of figure it out and go with from there. Cool. So, nice. Now, there's another reason we do Jacobians, and back in the day it was a lot more important, okay? Because obviously you got to do a lot of this stuff by yourself. So it was really simplifying, you know, the region that you're working over. But you simplified the region, or the integral rather, by transforming the region. So in other words, the region might have been bounded by something like this. In other words, it might have been some kind of this goofy looking parabola good Lord. You know it's time to go back to take the rest of the summer off. This parallelogram might be my region. Okay? But my region, is in the XY plane. Okay, well check this out. If you're going to integrate over this region, you're going to have to break it into one piece here because there's a floor and a ceiling. Well, I'm sorry, ceiling and a floor. Another region here with a ceiling and a floor. And a third one here. And no matter what you do, it's going to be more than one. What if I did it the other way? What if I did dy dx instead? Well, you'd have to break it here. Here. Oh, it's still three pieces. Oh, it's terrible. Well, if you use a little ingenuity and the right substitution, you can transform this region into a region that looks like this. And how cool would that be? And so we would transform it from the XY plane to some UV plane. And in order to do that, you're going to have some clever transformations. Now, the good news is we show you how to do this, but the exciting, really exciting news is that we really don't do a lot of this anymore as a general rule. The general populace doing calculus probably doesn't do it, rarely does this anymore on their own. Okay? But there will be times when, in the course of some physics class or some electronics class or something, you might come across some deal where they've made some transformation and they've done it. Somebody in the past has done it and they said this is the transformation to use. And then the reason that they did that was to make the integrals easier to compute and deal with. Okay? So that's typically how these things were done back in the past. You got your slide rule and you need a better way to do it. So somebody in the back room, usually a math guy, because as my friend the engineer says, math PhDs, they work for chicken feed. So when we can't figure something out, we pay one of them for a few months or something. They figure out how to do it, and then we're good to go again. So there it is. So what we need is we need to have x is some function of u and v. And we need y to be some function of u and v. And then we'll just set up our Jacobian again. We'll have x's and y's. We'll have u's and v's, and away we go. Okay? And so this is how one of them is going to go down. I'm going to do an example of one or two, and I think once we do a few, you'll be like, oh, this is not that bad, and it really isn't. And so here it is. So I'm only going to do the ones that are actually integrating. Some of the other ones they ask you to do, or some of the other ones in the homework are, go ahead and just find the Jacobian. Well, that's lame. I'm going to do it all. So I'm going to integrate y squared dA over some region. And the region is bounded by xy equals 1, xy equals 2. Good Lord, I need my glasses on. Yeah, that's right. Xy squared equal 1. And xy squared equals 2. Okay, well, so I have no idea what that looks like. Okay? That's not true. I've done this problem a few times. It's one of my favorite problems in the book. But if you didn't know what it looks like, you just grab your calculator and go to work. So here it comes. Betsy Desmos. And that's the thing I like about it. I love about this calculator. I don't have to do any algebra. Solve for y equals. That to me is worth every penny of this thing. Voila. So then the question is, where do they all overlap? Well, the only place they all overlap, of course, is in the first quadrant over here. So go away. There we go. And so what we're talking about is the region from here, 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 and here. Oh boy, wouldn't that be fun to integrate over? You'd have to do it in 3 pieces. It looks like, three pieces. And we'll look at that in a moment when we get over into the notes page. But man, 3 pieces, I don't want to do that much work. So through the magic of the Jacobian, we don't have to. Okay? And this is how it's going to go down. Okay? Again, if you're doing it in the old school way, you'd have to break it here, here, and then you'd have 3 pieces. That's stupid. So what we're going to be told is that we're going to let x equal, or u equal xy, and v equal xy squared. No, that's cool. And so what's interesting on these is sometimes I see them, and sometimes it's easy the way these are written out. Sometimes they're not so easy. But if you look up here right now, that means u goes from 1 to 2. And that means that v goes from 1 to 2. So we've taken this goofy looking thing down here, this hodgepodge in here that we're trying to find the area of, and we've taken it from the xy plane to the uv plane, and we've made it something ridiculous like this. 1 to 2. 1 to 2. Integrate over that guy. Okay, that's awesome. Meaning we can do it all in one fell swoop. Now, but in order to do that, here's the problem. Remember I said this need to be x needs to be a function of u and v. Okay? And y needs to be a function of u and v. I don't have that. This is very important. I don't have that. I have it the other way around. So what I'm going to do is I'm going to take my TI-89 and I'm going to solve them the other way around. Now, if you're bored and good at algebra, you're more than welcome to do them by hand. And I can, but what I find I end up doing is I end up screwing it up sometimes because, let's face it, it's a little messy. So what you do is you say alpha u here equal, and make sure that you put x times y. That's a big deal. And then and is second math 8. And then alpha v equal x times y squared. And then I want to solve for, so comma, squiggly brackets, x comma y. Squiggly brackets, parentheses. So I get x is u squared over v. And y is equal to v over u. Okay. Now there's ways to do that. I mean, like this one isn't too bad because you could, if I wrote it like this, if you divided both sides by each other, you get v over u is equal to y, right? This one isn't horrible, but it's not great either. And if you plug that back into here and then solve for x, you can find what x is. They're not terrible to do by hand. It's just not a lot of fun. So then my Jacobian is, again, x and y, u and v. So with respect to u, that's going to be 2u over v. With respect to v, it's going to be minus u squared over v squared, I believe. The derivative of this with respect to u is going to be negative v over u squared. And this is going to be 1 over u. Okay. So if you take this times this, you get 2 over v minus, and then this times this, the u squareds cancel out, and you get, so it's minus, but there's 2, so they're already positive, so it's going to stay minus, and it's going to be 1 over v. So my Jacobian then is 1 over v. Okay? So then my integral, which was y squared, is now going to become y squared, so it's v squared over u squared, times my Jacobian. And I'm just going to throw the du dv on here, but you can do it in whatever order you like. And since they both go from 1 to 2, we take the integral here and we're going to get, so let's clean that up, it's v over u squared. Okay? Alright, the integral of u squared here is going to be negative v over u. Right? Right. From 1 to 2. And if you plug that 2 in for u, you're going to get negative v over 2 minus a minus v over 1. And that's here and that's there. And so it's going to be, so that's a half plus a whole v, so it's a half v. So 1/2 v. So then I want to integrate 1/2 v, and so that's going to be 1/4 v squared, I believe, right? Right. From 1 to 2. So 2 squared is 4. A quarter is 1. Minus a quarter. The answer is 3/4. Yay. Now, had we done this in here, we would have gotten the exact same answer. All right? Now, what I'm going to attempt to do, right, is, well, first of all, I think I probably should go back and label which of those is who. Okay? So I'm going to go back to Desmos and check those out. So purple is xy squared. No, purple is xy squared equals 2, and green is x squared y squared equals 1. No, xy squared equal 1, xy squared equal 2, and then, well, this is easy. That's xy equals 2, xy equals 1. Okay, so from here to here, okay, which is from 0.5 to 1, okay, because I'm just going to do this with respect to x. Okay, I'm going to break out my calculator here, do a double integral. Okay, and I'm going to integrate, and my function that I'm going to integrate is the purple one, which is xy squared. No, wait. Yes, xy squared. Oops, what are you doing? Before you do that, then, okay, so before I do that, I want my y's to be bounded by functions of x, right? So then you'd have to convert this to y is equal to, it's going to be 2 over x square rooted, right? Same with this down here. Y is going to be square root of 1 over x. And this is y equals 1 over x. And this is going to be y equals 2 over x. There we go. So I'm going to do the double integral of y squared with respect to y. Oops, with respect to y from, now we want to go from purple function, which is square root of 2 over x. Oops, darn it, that's the top function, stupid. I want to go from the green function, which is 1. No, I want to go from the red function, which is 1 over x. And then I want to do with respect to x from 0.5 to 1. 0.28-ish. Okay? All right, next region. Okay. Now, notice I don't have to change too much except the limits of integration. This time I'm going from 1 to 2 out here on the end. And I have to change I need to change from the red function, which was 1 over x, to 1 over the square root of x, right? Because that's the green function. I could write square root of 1 over x, but it's square root of just square 1 over square root of x. It would work just as easily there. It's the same thing. Whoopsie daisy. How about a little diamond green? 0.375 or 357, I believe, actually. Okay. And then the last one, we're going from 2 to 4. Keeping the same green bottom function, but we're changing to the blue function, which is 2 over x for our top function. And we're going from 2 to 4. Oh, why did you do that? God, you're stupid. .111. Now, if you hold your mouth right, theoretically, right, you should be able to add that plus that plus, oh, I already did that one. One more. Plus that. 0.75, right on the freaking money. But that's a lot of screwing around. Okay. Now, today's day and age with the calculator, doing all the extra integrals isn't that bad. Back in the day, that was kind of a mess to do it by hand. So it was easier to do algebra. I'm going to pause this for just a second. All right, here's another fun one. And so this one is number 20, right? Number 20. And so right. No, I lost my train of thought. Where did it go? Oh, I'm sorry. Number 14. That's the one I wanted to do. Sorry, 14. It's number 14. Oh, it's not in your text. This is in my old text. So I guess don't pay attention to numbers. It doesn't matter. So it's a double integral over some region. And what I want to integrate is x squared minus xy plus y squared dA. Okay, the region is x equals the square root of 2u minus 2/3. What are you doing? This is not the region. This is our. These are going to be our change of. These are going to be our functions of u and v. And for reasons that'll become quite obvious later on, actually. That's a minus right there. Okay, those will be our functions of u and v. But here's the fun part. So the region is, it's bounded by an ellipse. So x squared minus xy plus y squared equals 2. That's an ellipse. And if you're not sure what it looks like, Desmos pretty sweet for this. X squared minus xy plus y squared equals 2. That goofy thing. Now, you say, well, I could solve for y equals. You sure can, and you're going to get the guy from right here and right there. Okay? And it's doable to do it that way. It's messy. All right? It's just messy. So, what we're going to end up doing this time is we're going to convert that goofy-looking ellipse. We're going to end up converting it into a circle. Okay? And if we can convert it into a circle, so we can then go from, probably what we're going to end up doing here is going from xy, which is, this is xy, to uv. And then because it's a circle, we're going to convert probably to r and theta. Okay, just to make it easier on ourselves. Okay. Now, the game is as follows. Well, we could do it that way first. I'll leave it that way. So let's see what happens when you take this thing right here and square it. You get 2u minus 2 over the square root of 3 uv's plus 2/3 v squared. And then we're going to get a minus xy. So this times this, oh, that's the square root of 2, is going to be 2u. Because it's this times this, and because they are differences of squares, there'll be no middle term. And then it's going to be minus 2/3 v squared. Okay, and then the last one is going to be this thing, squared. So it's going to be plus, and then it's going to be 2u plus 2 over the square root of 3v plus 2/3 v squared. So you do the math on this. Subtract that negative through there, distribute the negative, right? And let's see what we end up with here. We end up with a 2/3, a 2/3, and a 2/3, which is 6/3, which is 2v squared. Okay? Remember this equaled 2, so equals 2 still. And if you add up your 2's, you get 2 plus 2 is 4 minus 2 is 2. God dang it, those are u squareds. 2u squareds. And then these dudes cancel out. Yay! Look at that. U squared plus v squared equals 1. So we took this nasty thing up here in the xy plane and made it just, you know, this little cute little u squared plus v squared equals 1. Awesome. Now, good news. No, fabulous news. This thing right here is the same as that thing right there. So my integral becomes the integral from, well, it's just 2u squared plus 2v squared. Remember, you can't get rid of it. Here it was equal to 2, so I was able to simplify it. Got to leave it like this time. Got a little du, got a little dv out here. Okay. We'll worry about what's going to go here in just a jiffy. I mean, we'll actually figure that in just a minute. But actually, we probably won't actually figure that in a minute. We'll see what happens here. Okay. So then that's all fine and good. So then, well, actually, we do know what goes here. Technically speaking, this would be, the way I have it written, it'd be 1 minus v squared, 1 minus v squared, and then negative 1 to 1, right? Whatever. Okay, we'll worry about that in a second. But what we need to worry about right now is what goes right here. We need our Jacobian. So here we've got x's and y's, u's and v's. So if you come up here, what is the derivative of this with respect to u? It's the square root of 2. And then negative the square root of 2/3. And the square root of 2, positive the square root of 2/3. Okay? So you're going to get this times this, so it's going to be 2 over the square root of 3, right? Minus a minus, so plus 2 over the square root of 3. So 4 over the square root of 3, that's my Jacobian. And it's nice and clean, so of course you could drag it out front. Okay? Now the next thing I'm going to do is I'm just going to go ahead and convert this. So here, my x, I'm just going to let this pretend like that's my x. I'm going to do r cosine theta, and y and v equals r sine theta. So, and so here what I'm going to get is, it's going to be 2r squared cosine squared theta plus 2r squared sine squared theta. My 4/3 is out front, whatever, right? I'm going to get an r dr d theta. My r is going 0, 1. My theta is going 0, 2 pi. Okay? Well, if you think of it, they have a 2r squared in common. You'd have a cosine squared plus sine squared left. So what you have inside now is it's 2r squared times r, or just 2r cubed. If you integrate that with respect to r, you're going to get r to the 4. You're going to get a half of an r to the 4. And you're going to go from 0 to 1. So, of course, that's just 1. So then it's 2 over the square root of 3. Okay, that's what you'll end up with here. And then from 0 to 2 pi of d theta, so that's just theta, so it's going to be 2 pi times that, so it's going to be 4 pi over the square root of 3. Okay, answer. Oops, darn it. One more example, I think, for today is probably sufficient. Once you've done a few of them, all you can do is do them yourself and have fun. Let's see here. Suppose you do over some region, and we're going to go x minus, what did I say? X minus 3y? Yes, x minus 3y dA. And, ooh, cool. So we're going to integrate it over the region with vertices 0, 0, 2, 1, and 1, 2. And we're going to let x equal 2u plus v, and y equal u plus 2v. So you can do this in any order you want. You can substitute in first. Great. 2u plus v minus 3 times u plus 2v, which of course would be negative 3u. So it's going to be negative u. It's going to be a minus 6, so minus 5v. Right? That part's done. Good for us. Moving right along. Heck, let's go find the Jacobian next. So x and y, 2, 1, 1, 2. So 4 minus 1 is 3. I'm going to pull it out front because it's constant. And little du dv action. Okay? Now, think about this for a minute. If I make these points on here, it's going to be here and here, and here and here. So I need the equations of those lines. Well, this guy here, oops, this guy here on the bottom is y equals a half x. This is y equals 2x. And this guy here is, I don't know. So I can't get my head. Down 1 over 1. I think it's y equals 3 minus x. Yeah, it is. This is y equals 3 minus x. Okay? That's the region we want to integrate it. Again, if we're doing it, we could do it in 2 pieces easily enough. It's just I don't want to. I probably would never use the Jacobian on this one because that's just too easy to do it in 2 pieces and call it good. But there it is. All right? So, well, what am I going to do about that? Well, here's the deal. I could find out what u and v are. So if I know what u and v are, right, then I can plug in some values and see what happens here. For instance, so let's solve these guys for u and v. Oops. No, that's right. Stupid idiot. Oh, shut up. Y equals u plus 2v. And so there we have it. So it's 2x minus y over 3. And v is, I'm just going to call it 2y minus x. It looks easier to write. 2y minus x. Again, I think it was over 3. I wasn't paying attention. Yes. Okay? So I've got that region up there. How on earth am I going to find values for x? Well, check it out. If you plug 0, 0 into these guys, you get, well, 0, 0. If you plug 2, 1 into this guy, you're going to get 4 minus 1 is 3. 3 over 3 is 1. So 1. And if you plug 2, 1 into this guy, you're going to get 2 here and a 1 here. 2 times 1 is 2, minus 2 is 0. So 2, 1 became that. And 0, 0 became that. And so what does 1, 2 become? Well, 1, 2 becomes 2 minus 2 is 0. And so 1 here and a 2 here. 3, it's going to be 3 over 3 is 1. So that becomes that. So let's think about this. This triangle is going to convert to a triangle. No one's, I don't think, shocked by that. But it becomes this triangle. And this triangle can be done in one piece. This is what, not y equals, you jerk. Let's call this v and this u. This is going to be v equals 1 minus u. And then, of course, u is allowed to go from 0 to 1. And so over here, we're going to go 0, 1 minus u, and then negative, or 0 to 1. And again, I need to change this because the way I've done it, I did dv first and then du. Okay? So let's do dv first. That's going to be negative uv minus 5v squared over 2 from 0 to 1 minus u. I'm going to punt. I don't feel like it today. So what I'm going to do, a little integral, oops, down here somewhere, integral, and I'm just going to use x's and y's because it's too hard to go find u's and v's on the computer here. Okay, I'm going to integrate that with respect to y from 0 to 1 minus x, comma, with respect to x from 0 to 1, and times the whole shooting match by 3. So the answer is negative 3. Okay. Now, let's go up here. Should that bother me? I don't think so, because x minus 3y over this region is likely to give us negative y values, negative z values, yes? And that's probably what you're saying here. So a lot of negative z values. Hence, it wouldn't surprise me too much if our volume was negative. Okay? That's the game. Okay? So that's why we do it. That's the whole point of this thing. So that's 12.9. 12.8 is the same stuff, except it's all going to be spherical. And in spherical, it's always rho squared sine phi, and then get your d rhos, d thetas, and d phis on the end of it, and away you go. Oops, d phis on the end of it, and away you go. That's really the only difference between the two. Okay? And again, I'm not going to hold you responsible for spherical homework, because that's just kind of ridiculous. It's just not that hard to do. Oh, by the way, what would the Jacobian be in cylindrical form? Remember, cylindrical form is just polar form with a z on it, right? So think about that for a minute. Sometimes I forget to teach this because it's so easy that you feel like, whoops. But check it out. All right, so what is the derivative of this thing with respect to r? It's cosine minus r sine. So in other words, that part's all the same. The derivative of this of x with respect to z is 0. Same thing is true for y. This is sine theta. This is r cosine theta. So that part's all the same. And 0 and 0 and 1. So interestingly enough, when you do these problems, it's really easy to do because it's got this top guy, right, times these, so you get r cosine theta, right? So you get this times this, right? But it's times cosine of theta, minus, but then it's already a negative here, so plus r sine theta, times, and then you get sine theta times 1 minus 0, so sine theta, and then you get a plus, and then it's going to be 0 times, so plus 0. Well, that's the same thing we had before, and it's right. So the Jacobian for cylindrical is the same as the Jacobian for polar. So that's not that big of a deal.